Okay, welcome everyone to this recording of a talk that I'm going to give, hopefully around August 2026. Right now, when I'm recording this, it's April 2026. April and August, not a big difference, of course, but the field is moving very fast. I'm very confident that what I'm going to say is still accurate in August, but it's clearly not accurate at one point in my life or in life in general, and eventually of course, everything ages very badly. Okay, so let's jump right into it. So my title is very much over the top. I know quite a few mathematicians by nature, right? And most people, or almost everyone I know, agrees that AI will play a huge role in mathematics in the future. But of course, I can't speak for all mathematicians. It's more my biased perspective on things. And we will see this picture here in a second again, because this is literally how I think about AI in mathematics in 2026. And if I'm really honest, it's a constant trend which started about 5 years ago, roughly. It was around before, so AI in mathematics is nothing really new, but it really started off like roughly 5 years ago. So in 2021, if you want. And the slogan I really subscribe to is like this: a thousand things to check beats nothing to try. Yeah. Of course. So if you're hiring, for example, you will complain that you get whatever 1,000 applications, and it's so much work to sort through them. But it's of course better than to get zero applications. Yeah. And that's essentially why AI is so fantastic for mathematics, because essentially it gives you 1,000 options and 99% are shit, but 1% is good, which is still better than having no options at all, right? Okay, so this is really more like an overview talk. So it's based on work of too many people, way too many people. So not really my work, right? Just general. And since this is an overview talk, I somehow decided not to cite anyone, which is I don't know. We'll see. So it's really a huge community. Everyone stands on the shoulders of giants, and there's a big trend in mathematics that we have fewer and fewer single author hero type stories and more big collaboration type stories, which is probably just kind of the natural development of any type of field, essentially. Cool. A long disclaimer. Let me repeat. My title is a lie. I'm really just going to tell you about why I like AI in mathematics, and it's like very different from how you usually see the discussions about AI, general public type, if you want. Because in mathematics, we have a specific goal and it actually works really well. There's almost no downside in using it. There's always some downside using everything, but we'll see. So why the excitement is part one. So essentially, I'm going to do the following: why the excitement, and then I give you a case study. And I'm very biased. The case study will be about knots, because knots. Essentially, that's what it is. And yeah, so here's another picture, which is actually also a really good picture. Essentially the same flavor, right? You just get a lot of options. Most of the options are just absolute bullshit, but some of them are good, and you are able to check which ones are good. And that's just a cool tool. It's just a cool tool. I will zoom in into that. Not into that. I already zoomed in into the picture. I will zoom into the story a little bit further down the line. Essentially, on the surface, it looks like mathematics and AI should be like enemies of one another. Yeah, because mathematics, mathematicians like exact statements, right? That's essentially the definition of mathematics, and AI is really a tool to give you like plausible attempts. Huh? So, in particular, the large language models, they are really good in piecing things together and give you things that sound plausible. It doesn't need to be right? It's like a probabilistic machine, but it sounds plausible. And this kind of looks like a tension between the two, right? Mathematics wants kind of the opposite. But actually, and this is essentially, I think, you could turn off the video at this point if you want. This is essentially the message. Plausible attempts are actually really useful if you have a cheap way to just check which ones are shit and which ones are good. Yeah, then you just create, like in my picture up here, 1,000,000 plausible attempts, and you just sort out the good ones, and you're very happy. Yeah, and that's just so successful in mathematics. It's essentially why AI is so beloved by mathematicians, by more and more mathematicians. It's still an upcoming trend. So that's what it is. The key effect, which goes back to my little picture here, is the following. Essentially, and I've heard this many people saying in many different forms, so it's not just me. AI is like 100 unreliable but productive co-authors. Some people say, oh, I actually wrote 1,000. Anyway, many unreliable but productive co-authors, right? They like this. They generate a lot of funny ideas. Some of them have absolutely nothing to do with your problem. Some of them are pretty good, and it's you just need to sort in some sense. Yeah. Some people say they're like a bunch of enthusiastic students, or whatever. Essentially, it's this idea that if you want to build the pyramids and you are an Egyptian god king, then you just throw 100,000 people at the problem, and eventually you have pyramids. It's kind of the same idea. Nowadays, I'm very sad. Life is very sad. I'm not an Egyptian god king. It's too bad. So I can't just throw 100,000 people at my problem. And somehow AI is playing that job pretty well. So the analogy is a bit shaky, obviously, but kind of that's what I would like to have you in mind. And what makes this so good in mathematics, that's kind of roughly how we use AI in everyday life as well, right? But what makes it so good in mathematics is most of the time you can just see what comes out, look through the results, and you can kind of check which ones are good and which ones are bad. So it doesn't matter so much if it is often wrong, right? One of the big problems still of AI is that it hallucinates a lot. So you get a lot of kind of very questionable results, but it doesn't matter if you can just cheaply check whether they're correct or wrong, right? So that's kind of the effect, the key effect, at least in my very, very biased opinion, why this works so well. Yeah, so here my little picture with the little AI, very friendly AI, very, very enthusiastic, running around and creating ideas. I will give you, so the beginning of this talk is a lot of blah, 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 give you some more explicit examples as we go along. But essentially that's what it is. Yeah. So historically speaking, I think there is this myth that mathematics people think of, most people think of mathematicians as just calculating with large numbers. Some people have a bit more of an idea, and the next step on this ladder is that mathematics is about theorem, proof, next theorem. In particular, if you look at mass education, that's how it sometimes looks like, right? Theorem, proof, next theorem. That's not true. That's not true. The reality is what a surprise, there's life beyond theorems. Yeah? There's life beyond theorems, and there's life beyond proofs. And life is interesting. That life is interesting in its own right? So it's really more like examples, pictures, computations, simplifications, and a lot of false ideas. Oh my goodness. And sometimes you're just completely unproductive. You're just sitting around and staring at your screen and doing some brain rot instead of mathematics. That's how reality is. It's not theorem, proof, next theorem. That's very sad, or whatever. It is just what it is. And I think this comes from historically, at one point, roughly around Gauss's time. So Gauss is one of the big names, was really good at that. Mathematics went from a more explanatory style to a more polished style. So essentially you don't publish your failed attempts anymore, or your how you get there, or even examples. You just publish the polished statement. And it became kind of a big trend. It's going a little bit backwards nowadays. Nowadays, if you open a book nowadays and you compare it to a book 100 years ago, and they're still both about algebra, so there's essentially no change in the topic, you would see way more examples, illustrations, or whatever nowadays. But traditionally, at least going back to Gauss roughly, mathematics was really good at being very dry. Yeah? So that's, I think, why a lot of people have this impression that mathematicians are very dry. In reality, we really like examples and computations and conjectures, pictures, computations, simplifications, and a lot of bullshit that one produces from time to time. I produce a lot of bullshit. So here's a famous example of that. One of the first computer-generated conjectures, the Bayes-Dumont-Dyer conjecture. If you don't know what it is, it won't appear anymore in this talk. Very famous mass conjecture. Essentially, the blue points were guessed with a machine, not guessed, computed with a machine, and the guess is essentially that there should be the growth rate should be this line here, essentially, right? So computer-generated examples, and then there's a conjecture, and eventually the statement itself of this Bayes-Dumont-Dyer conjecture looks very abstract. That's usually what mathematics does, but in reality, it's really just there are a bunch of points and they fit into a line. That's essentially what it is, and it's a really good example. That's how mathematics works behind the scenes. Yeah? And yeah, as I said, it's kind of changing. You see more and more people actually revealing their cards, but of course, there's still a huge bias, if you want, in the system. And yeah, mathematicians don't really tell you in their papers how they came to the result, which is very, very sad. But anyway, there is life beyond. This was me rambling, by the way. There's life beyond theorems. And this is essentially where AI comes into. So most mathematicians at this point don't think of AI like, oh, please ChatGPT prove my theorem, but really more like, can you generate examples, counterexamples, maybe give me an idea, something like that, right? So the behind the scenes type of excitement, which mathematicians are very, very excited about. Yeah, I already said this, but I thought this picture was fun. This bridge will be closed for one day between October the 17th and 28th. So this sentence is not wrong, but it is a bit questionable because it kind of could be interpreted in two ways. So clearly between October 17 and 28 there's not one day, but anyway, just to distract you from the actual topic. So before anything becomes the theorem, right, there are examples. We already had that, and a lot of dead ends. And kind of AI will help you with the process of getting there, which most people are very excited about. We'll see. I mean, I give you very explicit examples in a second. And essentially what happens is the following. A lot of problems, oh, this is fun. Oh, this is such a fun picture. Apparently this bacteria, I will not try to pronounce the name, but the blue one, doubles itself every 20 minutes. And you're just like, what the hell? So you start with 1, then you have 2, then you have 4, then you have 8. And in very few minutes you have a lot of them. Oh, bacteria are fun. So in nature itself and in mathematics in general, you very often have way too many. I mean, it grows way too fast. You get way too many options. The number of choices just explodes. There's a name for it. It's called combinatorial explosion. So very often you get whatever. You check it by hand for 3 steps. Then for 4 steps, there's always so many options, and you probably don't do it by hand anymore, so you find a student to do it. For 5 steps, you can't even find students anymore, so you need a computer. And for 6 steps, the computer can't even do it anymore because there are way too many things. And standard examples where they're easy to understand, like knots, graphs, groups, all of these grow like, oh god, they grow so fast. Right, so the rules are exact, of course. You could, in principle, write down n equals 6 or n equals 7, but the number of choices is just too big. Yeah, and essentially this is where the opening comes in, where AI is so helpful. It kind of is very patient with large scale things. And this is kind of a really important point that I want to drive home, so I take some time to explain it. If for most problems I have, there's of course a finite number, not of course, but there's a finite number of options, but the number is so large that I just can't list all of them and run through all of them. And also the things I'm looking for are so rare that I can't just grab a random thing and just study the random thing. It's just not going to happen. This is where AI comes into the game. It makes kind of smart guesses, if you want. So it avoids the problem of this ocean of options. Yeah, and in some sense, this is how it's supposed to be, because if you could solve the problems that AI is solving nowadays using just a brute force, I list everything or I do it randomly approach, someone would have done it already, right? So these type of questions are already kind of solved. The whole point of AI is more like there is this ocean of options, but there are still some really tiny patterns which you can detect, and AI will kind of pick out these patterns. It still does a million of mistakes, but that's fine for, because it can just do a million operations per second or something. It doesn't matter if it does a million of mistakes, but it still finds the correct thing, and this is what makes it so valuable. And this is kind of a standard thing, and that's why I have this picture. The explosion of choices is kind of a standard thing in mathematics and the world itself. So I'm still surprised that this bacteria actually doubles itself every 20 minutes. Very, very efficient. Asexual reproduction, very efficient thing. We should all do that, actually. But that's just me. Right? So that's what I'm trying to say. There's structured chaos, as in this picture. So I struggled a long time to find a good picture of structured chaos. I thought this was a good picture of structured chaos. It's kind of a bit chaotic here, this little settlement from upstairs, but there's also some patterns. Right? So this is kind of where AI is really good. If there's plenty of choices, so way too much to list them, to do it by hand or do it randomly or anything like that, but there's still a little bit of a pattern, right? If it's just white noise, there's nothing you can do. But if there's a little bit of a pattern, kind of AI might pick it up and actually give you some reasonable, right, examples. That's the whole point, right? And then it does 1,000 attempts, and that's why I have my subtitle here. I actually don't need to scroll all the way up. Oh no, now it broke. So the file, by the way, is very large, so if it breaks from time to time, that's just what it is. I have it down here as well. Look at that. Oh, it even goes back to the... Oh, I didn't know that. Excellent. So the subtitle is 1,000 things to check. So it generates 1,000 things. Most of them are a little bit weird, but some of them are good because it picked out some very tiny patterns. Yeah, and then you can just check those. And if you would just, I said it again, if you just would generate 1,000 random examples, you wouldn't find anything because what you're looking for is still too rare. And this is exactly where AI is so good. Yeah. And again, we can easily then usually check afterwards why this works so well. So this is literally what it is. One more reason, and then why AI is so beloved in mathematics. And then I give you some examples. And then we go into some real examples, and my blah, blah, blah is over. So here's it's a really good illustration from Kantar magazine of the Fourier transform. Essentially, you have this function up here, and you decompose it into its elementary frequencies, and then the sum of all of these is that thing up there. The Fourier transform gives you a way to go from here to here and back, essentially. And the Fourier transform is one of the most important tools in mathematics ever discovered. And it's like used everywhere. Like Fourier transform everywhere. Of course, I could have just made a much easier example like the derivative. But I wanted to tell you a bit more of a fancy example of Fourier transform. What I'm going to tell you now is another reason why AI is so beloved. Because good tools are actually really hard to find. And this is kind of, again, a general pattern of life, if you want. Essentially, we are still driving the same cars as 100 years ago. They were just refined. So we're still kind of using the same tools. Good tools are hard to find, and they are just reused mercilessly, yeah? And good tools, there are not many good tools in mathematics. Yeah? It takes a while to understand. When you first grow up as a student, all the fields look so different from one another, but they're all doing the same in some sense. That's the whole point. Yeah? AI is a new tool. We hadn't had anything like that before, or not in the form we have it. It changes the search. And a new tool, people will use it mercilessly, right? Imagine you have 1,000 people to throw at a problem. Yeah, it's something new. As I said, in principle, I could also just be an Egyptian god king and throw 100,000 people at my problem. Turns out that's not happening, so I rather stay with AI. I tell you about the Egyptian god king and the ideas people have how to actually do that in a moment. But for now, AI is just cheaper to perform than throwing 100,000 people at a problem. Right? New tool. New tools are very rare. Please remember new tools. Right? New tools. I wanted to tell you about the tools on this screenshot, but I actually have no idea. I have no idea. I don't know a single. Maybe I know some of them. One of them looks like a drill or something. Anyway, so new tools, very hard to find, right? And AI is a new tool. So, and at least in math circles, it's a new tool. So the excitement comes from new nails. You can, no, sorry, you have a nail and now you have a hammer. So that's where the excitement comes from, essentially. Is there a hammer on this picture? I can't see a hammer. It's very sad. It's very, very sad. I haven't picked a good example. Let me give you an example. I haven't picked a good tool example. Let me give you an example how that works. So very, very famous. Why does it work? Same thing again. Very, very famous is AlphaEvolve. It's a pretty cool idea. Essentially, it's an LMM that plays evolution on Python code. Pretty good. So it plays evolution, not in the biological sense, but now you can make a program with itself 1,000 times. Yeah. Asexual reproduction, we all would like to do that. So you made a program with itself 1,000 times, or you can make 1,000 programs together, or whatever. Anything is possible. But you play the evolution game on Python code, and evolution is very, very strong. So you kind of get very polished Python code in the end, whatever your problem is. And they use that to solve these type of problems that you can solve by throwing 1,000 people at it. So here, for example, essentially, this is from, oh no, file is too big. This is from the AlphaEvolve paper. The hexagon problem. How many hexagons essentially can you fit into a bigger hexagon? And you want to minimize something. And they were able to go down from 4 to 3.94 to something like that, right? So using some slightly strange configurations. So it's kind of standard configuration human found and a slightly strange configuration that AI found. Similar problems. You can solve similar problems with AI, essentially. Show you some more examples in a second. But this is roughly the state. So almost everything you see in AI and mathematics is some variation of this idea to throw 1,000 people at the problem and find something someone just randomly found, essentially. That's just what, it's not randomly, right? There's a bit of human intuition involved, if you want, and that's exactly what AI does. Because I just contradicted myself if I would have said randomly, because before I wanted to make the point that it's not quite random, because random wouldn't give you enough, give you the correct results, and it's exactly true, right? So this is a pretty good example. Before we go into more details, let me just wrap up with a few more examples. I just put them on screen, and they all are in the same flavor. I call them honorable mentions. We do the one in the screenshot in a second. So you can read it here, but let me just show you the one that got me into AI. This is this fabulous paper by now like 5 years old from Adam, construction combinatorials via neural networks. Pretty simplistic neural networks, but it's a pretty cool idea. So several constructions, and it's kind of the same strategy, and you get real, so in this case you get real statements out of it, and I show you one example. So LM explains a little bit what's going on. I'm looking for a specific type of picture. This is very nice. So there's a certain type of problem, a conjecture, whatever, Adam wants to disprove. Where's conjecture? It's probably that conjecture, that conjecture, blah, 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 whatever, some number, blah. And you can disprove it by training a neural network. I hope I clicked on the right conjecture for that one. But anyway, you train a neural network, you give it a reward. Let's say if whatever kind of number gets close to, right, you want the conjecture to be false, so you want this to be smaller. So you give a reward the closer to you get to a smaller. And what Adam then did is, well, train a neural network, it guesses some graphs, it's really bad in the beginning, and it kind of learns and learns to get better and better and better. And eventually, as you can see here, so this is like the evolution, it kind of converges to something that I can understand, and then I could just go, all right, it will output these guys, and then I will just go and prove or generalize it, add more leaves here, and disprove the conjecture, which is kind of a nice idea, right? So it's kind of converging to something, and then you can just take it and disprove the conjecture. That thing. Similarly here, there's an evolution on these things for another conjecture, and eventually eventually you can just guess the example. So this one gets close, and maybe you have an evolution again, and you will see, maybe the counterexample should have a long string here and a long string here and a little bouquet here, and you just guess it, and you can just construct the counterexample. Yeah, this was the starting point for me. Again, this could have been something that you could have solved by just throwing 1,000 people on it, but in this case, you can actually solve it. Let's go back to Adam's paper by a machine. In this case, a reinforcement learning machine. And it's kind of a nice thing is, again, you at each stage you can easily reject the wrong things, right? You have that graph, you just compute the corresponding numbers. Where's my conjecture again? I hope it's the right conjecture I'm pointing at. You just check the conjecture again. There's some numbers involved. You check whether this graph satisfies the conjecture or not, and you can reject it and just keep on going. And it will generate 1,000 things, and eventually something interesting pops up, and then you are very happy. Yeah, nobody was able to do it before. So it's kind of a new tool coming up here in mathematics. There are many, many other things. I list some of them. One of them that I get very excited about nowadays is the gamification idea, right? Which is a modern version of I'm an Egyptian god king and I throw 100,000 people at my problem. Because you just have... Essentially, the idea is the following. You have a question, you formulate it as a game, and you hope that you can somehow let a lot of people play it, right? Gamers are very persistent. A lot of people play it, kind of collect the data, the high scores, or whatever you want. They create, and hopefully that they solve your problem, which is pretty cool. Pretty cool idea. So let me show you this thing, which I think is pretty cool. So it's here. It's called Unknotting. So if you are the creator, very unlikely that you watch this video, but please contact me. I'm very interested in gamification of math problems. And essentially what I have in mind is the following. So here's this Unknot game, which is a fun game. So you can pull your knot here, and you could flop crossings. You will see a crossing flop in a second. You can flop crossings over, plop, and then you can unknot it, and you're very happy you just found the unknot. Yeah, there you go. You found the unknot, so you kind of cleared the stage. Right? So then you can just, okay, fine, and you needed one swap. Cool. And why is this so cool? And you can do other things. Why is this so cool? Well, let's say you are interested in this unknotting process. Yeah? You get 100,000 people to play this game. They kind of swap crossings on complicated knots. And you immediately have a way to just verify whether... Well, it's immediate, right? You can just verify whether what they did was actually correct or wrong. It's very easy. And you then have 100,000 examples, and maybe among those 100,000 examples, you find something that you were looking for because actually you just phrased your problem as a game. Yeah, it's a very, very interesting idea, which I hope will get more and more popular as we go along. Right now, I don't know anyone who's really doing it. A lot of people talk about it, but I don't know anyone who's really doing it because, obviously, in practice, this is more difficult than just using some easy Python code to use a neural network to do something. But it's kind of this idea that human intuition in 2026 is still better than neural networks. So if the advantage of a neural network is that it can do 1 million things per second, maybe you just need 1 million players and they actually get you better results. So I would be really interested in doing that if you have some computer programming skills, so game programming skills. Let me know. It would be fun to do. But this is my modern version of the Egyptian god king who throws 100,000 people at the pyramid problem. And yeah, so that was a lot of waffle. Hope it was reasonable. Let me summarize. AI is so important in mathematics because it generates a lot of examples that you can easily verify, so you don't even run into the problem of hallucination or something. And it's a new tool that you can use, and people get very excited about new tools. And yeah, it's like having 1,000 people thrown at your problem, which is always very useful. Okay, let's continue. And I just realized, I should make this clear, that of course the strategy of throwing people at a problem, or maybe more general 2026, throwing AI at a problem, is not gendered. but I don't know any gender neutral name for God King. Is it a language gap or is it a problem on my end? Let me know if you have any ideas in that direction. Cool. Let's go to knots. So I'm going to explain AI problems, how AI can solve knot problems. So I need to tell you a little bit about what knots are, and it's fabulous. So the end result is so fabulous, it's absolutely bizarre what's going on. But let's do knots first. So a knot, excellent. So a knot is that thing here, right? So it's essentially a rope. I have my little figure 8 knot here. Can you see the figure 8 knot? Maybe, maybe not. I built it out of, I have no idea what that is. It's kind of a little ribbon type thing. It's a very nice knot. So what you usually do is you take like a ribbon or a string or a rope, like in the left hand picture, and you glue the ends together, like here. And you get a knot. Here's my little knot. It's supposed to be a figure 8 knot. Beautiful. This little knot thing has 2 sides. Very nice. So a knot is, well, literally that's it. So that's literally a knot. So it's an everyday knot, but you glue ends together because otherwise you would be able to undo it. At least mathematically, not necessarily in practice. So a lot of real-world knots, applications of real-world knot theory, are actually not these type of knots. They're just knots where such that the string is so thin that you can't easily undo it. So here, of course, if this would not be glued together, or here in my little thing here, if this wouldn't be glued together, I could easily undo that. But if you imagine the string is like really, really, really thin, then getting rid of a little knot is actually pretty difficult. So that's how it usually works in practice. But for mathematical reasons, we like to think about knot length to be just a closed string. Yeah, you just glue the ends together. Yeah, I want to make this very clear. Just glue the ends together here. I'm just really stupid. I just have a little bit of tape to glue it together. And literally the knot is just, I have a little video which is a bit better than playing around with the thing here. You can just move it as much as you want, and you can already see the thing that will happen is kind of the shadow that you see from here is like the projection if you want, and you can kind of change that and it will look very different. Oh my goodness, now I have ruined my figure 8 knot. What's going on here? I have no idea what's going on. Oh my goodness, it's so difficult. Oh, here you go. Anyway, and the standard question mathematicians like to do is they want to identify the knot, essentially. Yeah. So you look at one of these pictures and you say, oh, this is a trefoil. Something like this. Yeah. That's what mathematicians usually like to do. Okay. And there are plenty of interesting questions in knot theory. And the reason why people like knot theory so much is because you can build it. So it's very nice. It's not super difficult abstract, but there is still a lot of interesting mathematics, which is kind of a nice sweet spot. Knot theory is what people like a lot. Yeah, and I like it a lot. I mean, come on, I've spent something like 20 minutes. I'm very inefficient. It was probably 20 minutes, really, to build this thing. You could probably build this in 1 minute, but I'm just super inefficient here. Anyway, this is kind of a knot. I'll have a nicer video in a second, but roughly that's a knot. Here's another knot I built. This is a trefoil, and the basic game is, well, the string may kind of wiggle wildly, and what you see actually might change a lot. So here, the slides are very big, right? So here, this is also a trefoil, just a really shitty kind of. I just took this thing and I just shittily wiggled it around, and you get some pictures that look like that. Yeah. So while wiggling actually gives you very, very, very bad pictures sometimes. And kind of the whole point of the game is to identify the knot from a bad picture. Yeah. And this is just very difficult in general, and it's still very, very, a lot of fun, very, very playful. So as I said, people like that a lot. Yeah, so I give you a few more details as we go along, but right now we are in waffle mode, which is fine. Everyone likes waffle mode. And the way this works is, and maybe now it's a good time for the video, that instead of thinking about the 3-dimensional object here, you think about a 2-dimensional thing you can draw, and a shadow. Do I have a nice shadow picture? I do have a nice shadow picture, or something like this, yeah. So instead of thinking about the three-dimensional object, you think about the two-dimensional shadow of it, which people usually call a diagram of the knot. And as you can see, a certain knot can have many, many shadows, depending essentially where your light source is, how the string looks like, and so on and so on and so on. And turns out that on shadows, you have three moves, and knots represent the same shadow if and only if they're a shadow represents the same knot, exactly the other way around, if and only if there's a sequence of these easy moves. They're usually called Reidemeister 1, 2, and 3, and you'll see in a second why they're called Reidemeister when I'm going to play the movie, right? So in the shadow, the only additional information you remember is over and under, so you get these over and under type pictures of knots. So essentially what I want is a knot diagram, and you'll see something like this. Let's see. Do we have some nice image? Knot theory. A knot diagram, something like that, right? So, a little bit of a shadow of a three-dimensional object. Do we have some other nice knot diagrams? These are nice knot diagrams, right? So you remember the over and under type crossing. Let's have a look at the knot theory here. Do they have nice pictures? Yeah, that one is a bit easier to see, right? So this is a shadow of a trefoil, and literally only remember the over and under crossing type information. Okay? And then there are only three moves, these moves, and we'll see them nicely in action in this video. Not my video, I stole it somewhere, but I forgot where I stole it from. Anyway, so here a knot is this type of string, yeah, whatever, does something, blah 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 blah, and yeah, you can deform things, as you can see, you can do these, and the nice thing about the video in a second, that it will tell you each and every single move step by step, right? This was just still the same knot, but just a topological operation on the knot. And now we can have a look at the moves themselves in each step. So here a Reidemeister 2, which just pulls these things apart. This is a Reidemeister 1, which just gets rid of a kink. And now we see a Reidemeister 3, which is a little bit more complicated, but essentially I need three arms to do it. But anyway, essentially you have a crossing somewhere and something in front, say, and you can just move it around. And the magic of the theorem is the Reidemeister moves is that every knot, knots and knot diagrams are related exactly by the Reidemeister moves, in the sense that two diagrams represent the same knot. Here's a Reidemeister 3 move, if and only if there is some finite sequence of these moves connecting the various projections. That looks like a Reidemeister 2 move, and you undo it. Beautiful. And you look at, it's really nice here, it's like this local cookie cutter type thing, right? Every move is just local, and you can also apply the move the other way around if you want, right? So in this case, you added a few crossings, and this is literally why knot theory is so interesting, because you have those three moves. It's a three-dimensional thing. Here, good Reidemeister theorem for 1927. That's why they're called the Reidemeister moves. Let me just close the video now. Right, so this is kind of why it's so interesting. It's a pretty complicated problem, but you can draw it on a piece of paper, and you have like a combination of three moves. But the problem is there's like this tremendous search space of the three moves that you can do. So it looks very innocent, but very often in life you have an innocent looking problem that kind of gets complexity by just applying random things somewhere. Okay, so the same knot has very many different drawings, and some of them are just tremendously bad, just so bad. So here, right, so a photograph of a knot can be really bad. So this is from some biology paper. I think this is a knotted protein, and usually under electron microscopes you see some of those bad pictures, so you want to kind of have a method to identify the knot from a bad picture. Yeah, and you have no control whether the bad picture is bad or good, essentially. So some photographs are just very unhelpful in this case, right? This kind of the point. And here's one example which I really like. So this is an unknotted string. Yeah, this thing here is an unknotted string, and this is just a very bad projection of an unknotted string, right? Literally so bad. I mean, if I just give you this picture, I would think most people would say this is a knot, a real knot, but you can see here this beautiful sequence of moves that undoes it. And kind of very, very notable also for later is that there's not a single simplification move on this diagram to get you here. You have to make the diagram more complicated by adding crossings, by doing a Reidemeister 2 move the wrong way around, and then you can simplify it. Yeah, this is a local minima in a certain way. You can't get out anymore. You can't get out by being flat. You need to get out by adding crossings, and it just happens all the time. This is just a small example for the unknot of a really bad choice of diagram for that unknot. And essentially in all problems you ever face in knot theory, it's some way related to the existence of extremely bad drawings of the knot and extremely bad photographs of the knot. Yeah, so unknot is just that thing. And yeah, a simple knot can have very, 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 very complicated diagrams, and the sequence of moves is anything but obvious. Yeah, and sometimes you have to do something counterintuitive, like to add crossings to actually undo the knot, which is a bit of a strange thing to do, right? And this is why this is so interesting, visually appealing and still combinatorially exciting. It's kind of very good and counterintuitive, which is why I like to use AI on it. It's counterintuitive, and somehow AI is really good at these. But in the end, it's really just a puzzle with receipts, because you just have you can just verify every move locally, right? You have a Reidemeister 2, you have a Reidemeister 3 here. Actually, two of them. You have it here and you have it here. And yeah, if a machine can do it, you can just verify it. So this is a really good problem. Anything in knot theory is usually a really good problem. And not anything maybe, but a lot of knot theory questions are usually really good problems for AI. Yeah, and I can easily check that nothing illegal happens. So the point we had before, if the AI hallucinates, who cares? You can just verify it. It's easy, and so it gives you plenty of different options. So, for example, what people usually do is you have those fingerprints associated to it. Yeah, not invariant. Think of it like a black box. You feed into diagrams, you get out the numbers, say. And if the numbers are different, you are very, very happy, because then you can tell that the knots are different. It's literally a fingerprint thing. Yeah, literally a fingerprint thing. But it can happen that two knots have the same fingerprints. So people are always searching for more and more fingerprint type objects. So essentially everything in knot theory we know is in some way or form related to fingerprints, to knot invariance. But there's a kind of life beyond knot invariance, which is at this point very difficult to access usually. And this is where AI could be really, really helpful, and it usually is very helpful, right? And people really like to do this, just to say that. So here, an electron microscope picture of not the DNA, and then people draw it out very nicely and try to identify the knot using something like a fingerprint. If you know what a Jones polynomial is, they would compute something like the Jones polynomial. But again, this is cheap evidence you can just compute, usually to check whether the machine has not messed up. So in general, the point I'm going to make here is interesting problem, and usually it's cheap to verify whether the machine has not messed up, which is perfect for AI. And 3, it's a bit counterintuitive. We see more counterintuitive things as we go along. So very, very bizarre things are going to happen in knot world. And another point why this is so great, that you can just, this is something I would just zoom in, just take it for granted. So essentially there's a way to turn a knot diagram into a sequence of numbers. So perfect for a machine, and there's everything, just what I just told you boils down to operation on sequences of numbers. Perfect for a machine. Essentially how it works is you label the edges 1, 2, the segments of the knot 1, 2, 3, 4, 5, 6, right? And then around each crossing you see here 1, 5, 2, 4, 1, 5, 2, 4. Next crossing, whatever, you see 3, 1, 4, 6, 3, 1, 4, 6, and so on. And so you can encode all diagrams just in a very, very computer accessible language, And every funny move on diagrams is just some manipulation of numbers. So it's even easy to put most problems into a machine. Okay, diagrams can be encoded as finite combinatorial data. Same problem as before. The number of possible moves just is silly. It's just tremendous. You don't do that. And this is exactly why I can be helpful, right? Easy to encode, counterintuitive, easy to double check, and plenty of moves. Use AI on it. That's essentially the story. Why not theory is so well studied, and I show you two, as you can see here, two case studies in a second. But something like, oh, I show you this. This is so good. So here is an example, right? We already said that. Let me just read it out again. Exact rules, huge search space, checkable output, plenty of room for bad intuition, perfect for AI. And here's what I mean by plenty of room for bad intuition. So in this very strange illustration, very complicated illustration of a knot, you can see this little part here which sticks out. And you can just pull it in, right? You can just pull it in, as you can see here. Just pull this part in. But turns out if you flip this crossing, you flip it over from that to that, you would think this just gets stuck, right? You can't pull it out anymore. It looks like this before, and after flipping it looks like that, so you can't pull it out anymore. So it looks like locally it's just completely stupid. You've done a stupid move. You made it more complicated. You wanted to make it more easy. But turns out that then there will be simplification somehow coming from the side, and it's actually easy. The knot, if you flip this crossing around, is actually easier in some sense than the knot that you see here, which is just so bizarre and counterintuitive. Very, very beautiful. We come back to that later. But for now, let me just repeat here. Exact roots, huge search, exactly as before, right? What I would try to say. Exact roots, huge search space, checkable output, and plenty of room for absolutely bizarre operations. Okay, time for applications. Examples. And if you're following this channel, you will notice that I've talked about this several times before. The reason is very easy. I don't have many ideas. I actually have like epsilon many ideas, and I'm not even sure whether epsilon is 0 or the usual tiny bit bigger than 0. So I produce more videos than I have ideas, so it will be the same old shit in some sense. If you haven't seen it, welcome. So let's do it. It's actually fun. It's actually a fun application. Obviously nothing huge. Yeah. So most ideas are just epsilons. That's just what it is. They're not just epsilon many ideas. Also, most ideas are epsilons. Progress is very slow, but it's fun. It's fun. I had a lot of fun. It's kind of half-baked finished. I will comment on that as we get there. So in particular, if you want to join in, let's do it. I would be very happy if someone wants to join in. Okay, so standard problem, we have that discussed knots. Standard problem is something the unknot. Yeah. Can you untie a knot diagram? Find the minimal number of crossings you need. Things along those forms. And yeah, we already talked about this. So drawings are just combinatorial data. So essentially you just can feed it in a machine and ask questions. And the problem are diagrams of that form here. Yeah, so let's zoom in into the text a little bit. So I stole that from a really beautiful paper, Unknotting something. Oh my goodness, can I find that paper? Let's try to find that paper. Unknotting. Oh my goodness, what a hard word. Neural networks, maybe. Let's see. Yes, this paper here, really beautiful. Ooh, what the heck, really beautiful paper. So, I found it. Excellent. And they give a lot of examples of those diagrams of unknots that are just hard. And I explain the word hard in a second. At 42 crossing hard unknot diagram, so 42 crossings. So this is the unknot. It certainly doesn't look like an unknot. Oh my goodness. So, as I said, very counterintuitive, not theory usually. So this is an unknot. And hard, so they call an unknot hard, and I will follow that, and not just they. I think this terminology was around before, but they call an unknot hard Not just they, as I said. Anyway, and unknotted is called hard if you need to make it more difficult before you can simplify it. So there's no obvious Reidemeister 1 or 2 simplification here, so it's hard. Yes, and they call it very hard if Snappy is one of those programs that can do not, and as you can see, if it wasn't able to simplify it by just using that. So essentially, it's a very deep local minima of the problem. Yeah, and there are infinitely many of those guys, and they're just this is very nasty. So you might wonder whether a machine can help with this, because essentially the problem is the same as before. There's a huge set of moves you would need to try, right? This is your deck of cards, you need to make it more complicated and then to simplify it. But the set of moves is just too large. So here, oh god, so many moves. You can't do them all by hand, and it's super counterintuitive. I mean, what would you do here? I have actually no idea what to do. Maybe play around with this thing? I have no clue. I have no clue. And a machine might be able to do that by just creating plenty of examples and then eventually find a subtle pattern and try to do it. Yeah. So the action is essentially try one move, see whether it simplifies, try again. We'll be more precise in a second, but you could set this up on a machine. Yeah. Can you untie those very hard unknot diagrams? Seems to be a reasonable question. And the reinforcement learning translation, so here, just as a reminder, are our 3 Reidemeister moves. Yeah, the ones that simplify a diagram, and the one that I would call a shuffle. So here, the diagram has 3 crossings, and whatever, it has 100 crossings, and afterwards it has 100 crossings, but it somehow shuffles the crossings in. And again, I think of this as like a deck of cards, where these moves remove cards or add cards. You can read it the other way around, right? So you can read it from trivial to non-trivial. And this is a shuffle move. And that's what I want. So reinforcement learning translation. So I use the reinforcement learning approach here. If you don't know what reinforcement learning is, we'll do that in a second. So essentially a state is a diagram, and an action is one of those legal moves. And really we want an add or remove card move or a shuffle, right? So you build that up in a certain way, and the whole point of reinforcement learning is that you give rewards if you do something smart, right? And then eventually you just essentially that is how people learn in school. You give rewards if you have done something good, and you get penalties if you have done something bad, and you can do that with a machine as well. Yeah, and yeah, so that's just literally what it does. It essentially starts with some random, it guesses a random move. It doesn't get a reward, or it gets a reward, and just redo this whole process a million times, and then it kind of has to learn some patterns according to the rewards. And a reward in this process should be some progress towards simplicity, right? So if you successfully remove a crossing from a diagram, that should give you a reward. Yeah, so that's literally what it's supposed to be, but you have to be a bit careful because of the local minima. So just giving rewards when you remove crossings will not get you there, right? That's kind of the whole point. Hopefully that's reasonably clear. So I don't expect you to know a lot about reinforcement learning. It's essentially just you have certain actions and you give certain rewards, like a computer game. What the heck was that? That was interesting. Okay, so, and the point is, the trap is this thing, right? The trap is the best route may first make a diagram worse. So you can't just give it a reward for removing crossings. And that's why essentially you need to train it in a way, and you can do that if you give a reward for a successfully add, shuffle, remove, right? So you go a little bit up in your little picture. Let me see whether I can actually, what am I doing? I wanted to click here. You can go a little bit up in your picture if you do something like that, right? I think of it like a local minimum, whatever, something like that. And then down here it goes further down. So, and I'm stuck here, right? And I can't just remove things. So I do an add, shuffle. I think of the shuffle move as, because if I wouldn't shuffle, I would just add remove, which is a bit boring. So I do add, shuffle, remove. So that's my move. The add, shuffle, remove move. The add, shuffle, remove move. Oh my goodness. The add, shuffle, remove move. And AI will learn when to apply that if you just play the game. And you can literally set it up. It's not so difficult. And I did that, right? So you can do it. It works. And this actually works. So the move may look stupid. Oh, I actually have a picture. But it's literally that picture, right? The move may look stupid, but it's actually very smart because you're somewhere stuck in this local minima. And this is very counterintuitive, right? Humans like monotone simplifications. Not yeah, they're not like that. You're stuck in this. I have this picture here. You're stuck in this local minima type situation. So the machine gets paid to be patient, and the machine is really good at that. And it turns out it kind of picks out these kind of smart local minima move, at least on the test set, which is not necessarily generalizable to really, really, really large bet and not diagrams, but around in this regime of like 40 crossing, which is already pretty impressive, right? So 40 crossings is something you rarely see in knot theory. Most people stop around 10 crossings. Some people stop around 20 crossings. But 40 crossings is actually pretty impressive. So AI can do that, and it's kind of, you can program a reinforcement type unknotter, which is something humans can't really do, which is literally what you want, right? And you literally, right? You just want to do that, and it will find a way to go to the unknot. And it's not hallucination because you can just verify. You get the diagrammatic moves, and you can just check. Oh, but that actually works. And this is literally why AI is so good for problems of this form, right? That's literally what it is. So essentially, nasty diagram, and you can check every move. If it does something like that, oh, you just reject that, right? And otherwise, you just have nasty diagram. You do some moves. This one looks good, and then you just accept the set of moves. Right? It's literally the main problem the LMMs, whatever I have in real life, not in math life if you want, is that you can't necessarily easily verify what it's doing. And here it's super easy. If it's doing something stupid, you just reject it, right? And so the certificate is mathematical. You're very happy. It works very well. And I'll tell you in a second how well it actually works. It's pretty good. So yeah, we ran it, and it undoes. So those guys here in this beautiful paper, they have a set of hard unknown diagrams and a set of very hard unknown diagrams, and it can undo 100% of them, which is kind of a pretty impressive thing. And in each run, roughly, it undoes 95% of them. So sometimes it still gets stuck, but you just need to run it again, and it will get unstuck. So run, roughly 95% probability, but even better, the set of 5% that is not undone is essentially random, so you just do it a few times and everything is undone. Yeah? So it's really good. So the unknotter, which is pretty simplistic idea, if I'm honest here, just this idea, or maybe the bad move idea, right? So that idea is super successful. I was very shocked. So I think this is a cool application of AI because it literally just does something that humans somehow can't do. I think this is pretty cool. I call this thing the Unknotter. The machine learning. It's pretty good. I mean, and again, it's not super great. You can easily improve it. And I was just shocked how easy you get such a nice result in the end. It can undo very hard things. It finds very, very, very counterintuitive moves. So obviously, then you are just like, can I use that somewhere else? So I picked up another problem. And the same type of problem, there is this beautiful, absolutely beautiful breakthrough. Let me see where I can find that. Unknotting number not additive. From last year. Really, really absolutely fantastic breakthrough. So the unknotting number is not additive, and there was the conjecture was very old, and everyone thought the unknotting number was, or everyone believed, well, maybe I shouldn't say that. Most people probably believed that this unknotting number was an equality, but it's not. And the problem is this unknotting problem. I tell you in a second again what that means, or I tell you in a second what that means, is again very counterintuitive. So you're just like, counterintuitive moves. That sounds like and then you get certifications. That sounds like a good AI problem. Yeah, so I was just like, maybe I can do that. And this is a cool example of that. So this is a flop thing. We come back to that in a second. So the whole unknotting is you flop certain crossings, And you can literally see. So this is what the reinforcement learner in the end found. So here you can literally see you have this little bridge up here that goes all the way over. So you can just pull it away, right? So you think you just pull it away and the knot is easier. But for this unknotting problem, the smart move was actually to flop this crossing over, so that this piece actually gets stuck. That was the smart move. And this is again why this is so difficult, because who would do that? Who would do that? I have no idea, right? So this thing goes all the way over, and you have to swap this crossing. And before you wonder, why do you even have that part up here? You don't use it. Correct. So there's a bit of randomness involved. It does a bit of, it's sometimes over the top, right? You don't need that part. You only need this part, essentially. But you still need to flop the crossing over. So you have a bit of randomness, but that's just how AI works. So don't worry about too much randomness. AI does randomness. But anyway, so I think this is so cool. I will go into more details momentarily. But this is so counterintuitive, right? So you just have this situation where you can just pull away a string, very easy, and you do make it this, so you can't pull away anymore. The knot is easier. Oh my goodness, it's so good. Anyway, so let me explain what this is. So crossing flop, crossing flip, crossing flop, crossing change. I have no idea. There are so many names. It's literally you have this game where here's your knot, and you're allowed to flop a crossing, right? So here the red line goes over, and here the red line goes under. And then you can undo your knot in this case. So, and the game is to find the minimal number of flops until your knot is undone. And that is called the unknotting number. So here this says unknotting number 1 because it's knotted to begin with. You flop it over and then zoop, it's undone. So unknotting number is 1. And the whole point is again like unknotting numbers are, so this knot is easier, right? So unknotting numbers are kind of very tricky and very counterintuitive to compute, so that's literally what it is. And the question is, how, as I said, how many times suffice. So the unknotting number is the minimum over the crossing flops you need. Sounds reasonably easy. You just think, okay, here I have a 3 crossing knot, so I just test all possibilities to flop a crossing, and then I'm happy. The problem is this whole thing is diagram depending. So you can't just check a minimal diagram. You need to check all possible diagrams, which makes this extremely nasty. And this is essentially why our little problem here was so difficult, because the way they construct a counterexample is not on a minimal diagram. It's on a more complex diagram. So that's essentially what it is. So it's diagram dependent. So you would have to check essentially infinitely many options naively. Very difficult thing. So on one diagram, sure, you just flip whatever crossings you want, and there's a finite number of them, and you're very happy. You have to check infinitely many crossings. So that's why this problem is still unsolved for certain 10 crossing knots. So for certain 10 crossing knots, we still don't know the unknotting number. And again, if it would just be look at the 10 crossing diagram and run through all options, and that's easy. There are like 2 to the 10 or something options. That's not so many. You can just check them with the computer. But the problem is you need to run over all diagrams, and then you don't know what to do. So it looks like a perfect situation for an AI, because they're counterintuitive moves that you sometimes have to do, and you want to guess how they work. So the idea is, if you have a knot here, and you want to knot its unknotting number, you can't just naively flip crossings and see what comes out. But rather, you add crossings, let the you run a reinforcement learning guy again, and it kind of decides where to add crossings, and then you decides where to flop crossings. So this is an example of what I call an inflation of a smaller diagram. So it's inflated, right? There's this move that's completely useless. It's inflated over, but the swap is actually here. So that's why you need to inflate your diagrams, right? So you learn how to inflate your diagrams, flop a crossing, and then try to find it on the list. Because there's a list of knots with an unknotting number. So the idea is the following. I take my knot, K, and I want to know its unknotting number. Unknotting number of K is whatever, I don't know. Okay, I inflate it to K prime, which is still the same. I flop a crossing, I get L, and I find L on a list. U of L is whatever, M. What? Then I can conclude that U of K is smaller or equal to M plus 1, right? So I find bounds from, maybe this is small or equal, whatever. I found bounds for my unknotting number. I make it more difficult. I flop over a crossing. I try to find it on a list. And of course, I flop one crossing here, so I need to add one. And this strategy, which is literally, if you want an automated version of what they do, that's my interpretation, an automated version of they do, is so successful. It's unbelievable. And reinforcement learning kind of essentially comes in to guess a good diagram, to guess a good diagram to flop a crossing. That's what you do. The rest is more algorithmic. Yeah? So reduction is the unknotter, because you kind of need to, you blow it up to a crossing range where you don't have a list. So you need to reduce it to your list range. You need to use the kind of the unknotter. I haven't said that the unknotter is not just a verification for finding the unknot, but also it tries to find minimal crossing diagrams of a knot itself. So the reduction step here is actually the unknotter from before. Hopefully that makes some sense. And the problem why this is so hard is, as I already said, the same knot has infinitely many drawings. You would need to check all of them, right? And usually the flops you need to do, like this guy is it's so bizarre. It's so bizarre, right? So you have this funny move here and you flop it over here and the thing gets easier. So bizarre. Yeah, so the moves are very bizarre that you need to do. And it's just perfect for, here's another difficult diagram. I didn't know what to put on this slide, so I just put another difficult diagram on it. Right, so the unknotter, the agent, the new agent which uses the unknotter is not proving the unknotting directly. It's kind of making good guesses, get an upper bound, and hopefully you also have lower bound, and then you could get the unknotting number. And it works really well. It works amazingly well. Right, it's kind of the same type of process, and we found plenty of new knots. Unknot for an 11 crossing knot already, where it was only known that it was somewhere unknotting number was either 2 or 3, and if you then find the verification for 2, you're done. Unknotting number is 2. There are plenty of improvements, and we have even plenty of more. So it's pretty good actually. So yeah, so what I'm still planning to do, can we fit this on the page, is I really want to complete the I haven't done that yet. I'm just too slow. I really want to completely automate this additivity problem, right? So right now, my little unknotter here, this thing here, runs only on prime knots, and it kind of gives new bounds for prime knots, which is kind of good. People weren't able to do that, and because of the moves are so bizarre that you want to do. But of course, I would just want to automate this and then just find unexpected unknotting numbers. And kind of this very interesting thing, the way they do this is, so in the original one, they have, well, let's just click on it. Blah, 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 blah. Let's zoom in. It's a really beautiful paper. You should read it. Okay, so this is a conjecture. Conjecture is wrong. And the counterexample they find is 7-1. So a 7 crossing knot. You do it with itself. You have a 14 crossing knot. That thing is supposed to have unknotting number 6, but they found a witness of unknotting number 5. And what brought me into this is that this witness that I had on one slide at one point, I think I did it, this one, the witness where you have this fun crossing flop, right? So the witness where you have this fun crossing flop. So this is 7-1 hash 7-1 is on a god knows how many crossing diagram. It was 56 or something, right? So completely inflated, and you have a fun swap. That's why this problem is so difficult. So I hope to just set it up with this thing, which works really well on prime knots at the moment, and it eventually will hopefully also work very well on connected sums. Anyway, I hope you enjoyed this video, and I also hope to see you next time.